Great. I'm going to go ahead and start here. Thank you, everyone, for joining us today for the final talk of the Spring Design++ seminar series. This is our last talk of the semester, and we get to round it off with a talk from Fiona Collins, who I'm happy to have met at our AI plus X Summit, which was at the AI plus X Summit workshop, which we host. So we invited some members of our industry partners to give inputs on their work in AI. And at that talk, I thought, okay, we have to have her for an extended talk in our seminar series. So thank you for also agreeing to come here today. Great. Yes, we'll hear more about building spatial intelligence from measurements. And just as a quick overview and background about Fiona, she is a machine learning research engineer in the Innovation Hub at Hexagon, where she works at the intersection of AI, reality capture, and the built environment. In particular, she is developing intelligent methods for interpreting spatial data, bringing sensing technologies with bridging sensing technologies with engineering workflows. She holds a Bachelor's of Science in Environmental Engineering from EPFL. And she was here for the MIBS program, which also some of you might know her from, here at ETH Zurich. And she is also currently finalizing her PhD from TUM at the Chair of Computing and Civil Engineering and with Andre Borman. So I think that's also quite exciting that you're simultaneously working on your PhD. So with that, we're very happy to hear from you today.
Thanks a lot, Daniele, for the introduction. And welcome, everyone. My name is Fiona, as I said, as Daniele introduced me. I'm very happy to welcome you all to my talk today, Building Spatial Intelligence from Measurements. Let me take you back a step to where my whole motivation for this journey started. On the slide here, you see a ventilation flap. Why? It's a weird, funny object to start a talk with. Well, actually, it's a small object in a part of a big mechanical system in buildings where performance matters, right? It matters how the ventilation, the heating systems, etc. Work and how they perform for the operations of the building, for costs, for the energy footprint, etc. So it was back in 2019 when I was working as a working student in Siemens Smart Infrastructure while being a MIB student here in this building, actually. And we were tasked to build a building twin, okay? So at that time, this consisted of taking 3D models from planning construction, Siemens being the last kind of specialty planner in this cycle of construction, and then onboarding them onto the building twin platform where they would be coupled with the IoT systems. So complex systems of sensors and actuators communicating with each other and ensuring a proper functionality of the building. So the IP addresses of sensors were linked with items in the 3D model, typical kind of building twin platform. And we noticed that there was one building that was somehow not performing well, at least not to the standards that it was supposed to, and not to the standards it was certified for. So we had a closer look at it, and it turned out that there was those flaps, those ventilation flaps that were not opened at the end of the construction phase when the building was commissioned and taken into operation. It's a simple error. It comes from this sequential construction process where the HVAC engineers or the HVAC technicians set it up. They left the flaps closed not have any debris or dust accumulating in the ventilation ducts, but then subsequent specialist parties did not have the expertise or not the attention or not the authorization to modify anything. And in the end, without a check, the building was taken into operation. So luckily in this case we found it, but I was wondering how can such things be prevented? And I think at that moment, if we had had an asset scan, which would allow us to also see what is actually in the real world, a lot of things would have potentially been different. So scans existed at that moment. Large-scale terrestrial laser scanner was common. We had scans as well. However, those scans were relatively, let's say, dumb XYZ raw point measurements. And they were relatively large and cumbersome to work with, since they were hosted on desktop computers. So in order to detect such faults in the installation of systems, we would have had to overlay 3D model with reality and check, visually go through the different stories and check what is not correct. And that led to the fact that often those point clouds, they were, if one had to clean up storage space, they were deleted again. So I think it was at that moment that I probably signed some pact with some reality capture gods or whatever, because after that moment in time, I somehow never lost my fascination for this topic of reality capture, and point clouds have never left me. So now following that, I signed up for a master thesis and then 5 years of PhD studies to actually go into depth of what is reality capture, what are point clouds, what are images, and what are AI methods that we can use to enrich them and have a closest gap between the digital and the physical. Okay, and now I am in a company that has this reality capture at its core. Hexagon is the world leader in precision measurement, LiDAR technology. That all of this might ring a bell. And reality capture has come to a whole different level of maturity. So the size of those point clouds has not become smaller. No, it probably has even become larger. However, we have become more smart to deal with those kind of data sources. So if you can imagine here such a plant setting, this is not a few tens of meters, but those might range into 200, 300 meters in either side. So those are extremely large scenes, points. We don't even want to count them, and extremely intricate structures that are intertwined and sometimes even for a human relatively hard to grasp. So in Hexagon there is a cloud and software portfolio which is capable to deal with those kind of sources. And just to give you an example, for instance, with the cloud setting, those point clouds, they can be streamed onto desktop applications, so into BIM authoring tools or other applications where the data doesn't have to be hosted anymore on the device, but just parts, subsets, filtered parts of the point cloud can be directly worked with in engineering tools. So here, what is still missing is what we were talking before, somehow an intelligence to this point cloud, right? So XYZ raw measurements, this problem we have not solved. However, here is an example what we can do with analytics. So with AI solutions, which can analyze the points or the images that were also taken in the same scan and attach a certain meaningfulness to points, gathering them into objects, for example, or semantic classes. And in this case here, we can start managing this scene. So objects can start to be coupled with IoT systems, for example, or we can think about how to navigate to those objects for repair missions. Objects can be counted, they can be filtered out, or they can even be moved around, maybe cropped and moved around, tested in alternative scenarios, etc. So how did we get to this kind of analytics? And for this, I want to bring you through a brief history of how we taught machines to see over the last decade. So everything kind of started off with in maybe around 2015 when the first convolutional neural networks came out and the first data sets came out which allowed machines to train on this task. So semantic segmentation was, I want to start with that. With images, you can see the objects were starting to be identified, masks were laid on top of images. And in point clouds, this happened a few years later with point nets, where the hypothesis was generalized into the 3D space. Here you can see now objects are can be ordered into different semantic classes. However, we cannot yet tell objects apart to say this is chair number 1 or chair number 2. So what followed afterwards is instant segmentation, so telling objects apart within one semantic class. You can see again that first the advancements were done on 2D, and then shortly after there were also instant segmentation on 3D point clouds. This allows now to really distinguish objects one from another. This brings us to what some people might name as a turning point, and this is the publication of so-called foundation models. And this is where we don't talk about fixed class sets anymore, but we have models that have been trained on enormous amount of data sets with a very big diversity within them, and they start to generalize to objects that we have not even named to be important. And in fact, those models, they establish a latent space where in a very high dimensionality, they can cluster objects into similar parts. So here you can see, for example, this level of granularity at which those models operate now. Okay, this is Dino V3, which is the third version of a series of other models, but you can see how much detail it can distinguish. So the red point is always the one we're taking reference to, and the heat map basically shows the other pixels that are the most similar, or in yellow, the most similar to this query point. So you can see that bananas and melons and figs and oranges, they look different in this semantic space. Now, next to those representational models that we see with Dino V3, there were also other models that came out in similar times, which couple this visual space with the textual, or with the text space, so the language space. It means that we can start to find text representations and image representations of the same object in a close range within this latent space. This allows for use cases such as querying an image with a specific text prompt. Now, we can see this paradigm shift also going into 3D. So after some time, again, 3D engineers have taken this concept and proved that it also works to a certain degree. The models that operate now in 3D, they have the possibility to also include geometry, structure, and potentially also context. And you can see here, okay, basic objects, not a very large point cloud, but the results look convincing. Now, in most recent times, I have come across this article, 2026, which claims to align not only image and text space, but actually one more domain, and that is the CAD space, so computer-aided design. This is an area that becomes or starts to probably ring a lot of bells in your head, because it is the format that engineers work with, or one of the formats that engineers work with. And what was before perception and visual becomes now maybe in reach with also engineering formats. I have to maybe explain a little bit here this visual. It's actually, I think, still a very simple case of what a CAD object is represented as. But this toy object at the top left of the car is proven to fail, or previous methods in the second row show that there is no similarity between parts of the CAD object and a real scan, versus in this new publication they claim that those parts of the CAD and the point cloud do actually exist in the same region in the latent space, visualized by this hot region in red. So this looks fairly promising, but I haven't tested this method myself, so I can't really tell you how far we are actually to going forward on this. Now, there is still obviously a gap between the research methods that I've shown you and the real-world products that Hexagon tries to build to really bring real-world outcomes to the world. And those I summarize here as those two. First of all, the generalization to real-world data. First of all, the methods that we showed until now, they were mostly working on visual domain, and they were using RGBD scans, for instance, and they don't work with LiDAR scans the way that Hexagon kind of structures its portfolio. So here there is a big gap to what our clients expect from us and what we can directly take from literature. Similarly, the scale, as I already said before, we're aiming at point clouds that range over really, islands or cities and not just simple apartments. And another part is the industries with privacy regulations. So there's a lot of data, for example, in industrial plant settings, etc., which is not on the internet. So foundation models, they tend to fall short in those categories. At the same time, the value in engineering workflows, I think there is still a big gap of how to transform this kind of ordered point cloud into actual structured, topologically rich and constraint-rich 3D models for engineers. So I will go on to the next section, and that is more on how Hexagon turns AI into outcomes. First of all, giving you a little bit of a hint on what data and sensors we're working with. So Hexagon, as I said, is really good at measuring very precise points. Some of you might know some of those solutions on top the terrestrial laser scanners. The strong or the biggest of which can measure up to a few or half a centimeter over a distance of 270 meters. So extremely high-performant, long-range precision devices. With the mobile scanning, you might know some handheld, flyable, or also quadruped-mounted scanners. The ones on the right are the ones that can be mounted on cars for road scanning, for example, or into helicopters or airplanes for really terrestrial mapping. So this turns into point clouds like this. You have seen it before in some other of my pictures. And the basis of our, in the end, outcomes is, of course, this big competency of performing analytics on point clouds. We're here talking about big scale, really large number of points, but providing a lot of value to our engineering workflows. And the way it looks is that we can attach meaningfulness either on a semantic level or an instance level to those objects. Here you can see how the steel structure is segmented into different types of steel beams, and potentially here you could imagine how this other classes could be filtered out, and the focus could be laid either on the whole structure or just on a simple structure. It becomes maybe more visible when I show you an example like this, an object that reminds a little bit in its intricacies and in its scale to the ventilation flap I mentioned at the beginning of my presentation. So the ability to really identify small and fine detail objects at the same time as very large objects such as steel beams or extremely large tanks is definitely something that is a challenge, but well tackled within Hexagon. There are also some solutions that involve more user involvement. So for example, in point cloud cleaning and preparation, here you can see how a foundation model is used to support this workflow in manual point cloud segmentation. Going forwards to sites, here you can see how in a factory setting, which is actually one domain where there are frequent revamps, frequent retrofits, where the indoor arrangement of objects correlates with the production line or with the produced product. So with different product cycles, the indoors have to be revamped frequently. So here you can see how a lot of the indoor clutter has been removed, and we simply are left with the structural parts of the building. Those can be used like in a scan-to-BIM workflow, like is depicted here. Again, you can filter out all the object classes that are not of importance to you, and you can start performing scan-to-BIM in a semi-automated fashion where the modeling is informed by the object's geometry and semantics and can be traced relatively quickly rather than to a non-analytics based workflow. Here you can just see how these pipes, in the end, they can be exported and then fed into a BIM modeling tool such as Revit, I think Autodesk, and our fully modifiable Revit families in the end. Okay, so I go on to the next example on the city scale. There is the city Klagenfurt in Austria, which has committed to the EU mission of becoming climate neutral for smart cities. And the goal here is to have by 2030, 100 cities that have adopted certain green standards to be inspirational roles for other cities to roll out by 2050. And Klagenfurt has committed to scanning their city every, I think, 24 months, if I'm correct. And they can monitor, firstly, they can do a lot of potential assessments, but then they can also monitor the progress that has come with adopting new technologies, such as, for example, solar potential. So here with analytics, the total area of roofs can easily be calculated. Simulations can be done, and in the end, the progress can be monitored, and direct data-driven takeaways can be made on the city's progress. So this, in this case of solar adoption, for example, is based or can be proven with data that there was a 33% faster adoption rate of solar panels and solar energy provisioning compared to other Austrian cities. Maybe you might ask why we need such a high-resolution scan for solar, calculating solar potential. There were also other experiments done, such as wind tunnel experiments, etc. Wind tunnel experiments where the detailed geometries were actually important and yielded some surprising outputs, which, especially in intricate historical downtown settings, were not necessarily the ones that we would have expected with a local experiment. Okay. Then another part that's important for Hexagon is AI on the edge for the built environment. So here I give you a few examples. I want you to focus on the picture I will talk about, and so we will start at the top left. This is a total station. It's an electronic, a high-precision electronic survey instrument, which is used, for example, on construction sites to determine very precise points on where construction should start or where it should extend to. In infrastructure projects, this becomes also very important, where it's critical to have proper alignment. Also in sports, for example, this is used in the Olympics to, for example, measure the exact distances. And here the critical part is that the prism is properly set up, because if this wrong setup is chosen in the total station, the whole measurements are off. And you only realize it in the office, so you have to go and do the scan again. So this total station now has the capability to detect on the edge, on the device, which prism is in its reach, and it chooses the right setting and function of it. It can also track the prism, so in case you pass behind a tree, you lose sight to the prism, it follows it directly. Then there is the ARC module, which some of you might know from collaboration with Boston Dynamics. I'm talking about the two images on the bottom. The BLK ARC module was a scanning module that was designed to be integrated with robotic carrier solutions. The goal was to really bring laser scanning onto mobile platforms, move them into environments where humans either don't want to go or cannot go. You can see the dog in industrial settings where continuous monitoring might be of importance, and efficiency is highly increased by having robotic cycles of scanning. Also the BLK2Fly, where the drone carries this laser scanning module, and for example, construction progress monitoring can be done. On the top right, you can see the most recent big product that Hexagon has announced, published, and is at the moment rolling out. And it's the next generation of putting sensing technologies on autonomous platforms. So this robot is actually equipped with an enormous amount of sensing equipment, ranging from LiDAR, RGB, at different points around his body. And it's really taking the spatial AI to a next step. It's sensing its environment with the idea to interact with it. So picking up devices and helping us in the scanning in the automotive industry, but also being reactive to adapt when it sees something coming into its way, and really reason about it all. So I come to my conclusion. On the way towards spatial intelligence for the built environment, I have summarized a bit where we stand today and where I think maybe this will lead us in future. So as a bit of a recap, I think AI in Hexagon is a part of our daily dialogue. So some of our product owners, they say that they cannot really have a discussion with the client without mentioning AI, and this is in reality capture. So this is really starting to be business as usual. And the measurement outcomes, they're tangible. So fewer errors in the field for when humans are working with our devices. Reduced modeling times when we think about scan-to-BIM workflows, or increased adoption rates when we remember the solar panels in the city scale. Also, the progress that has been done in literature has, of course, been extremely rapid in the last few years, but it has also been a big accelerator in bringing up new use cases, but also automating certain workflows and freeing up time of workers to think of other things that they have previously not had the time to do. So for what's in the future, I think the gap to real engineering models is still something that we have to focus on. Geometry alone, perception is one big enabler, but in the end, having proper topological models with constraints that are the basis of simulations or fabrication processes, this is a place where we still have to improve. Also, the generalization, even if I have shown that foundation models, they are capable of achieving astonishing things, there is, of course, a long tail of very custom objects, which we have to be able to either involve or make human-in-the-loop kind of workflows, or having a methodology how to tackle such custom objects. And beyond this, I think in robotics fields, the reasoning is something that comes up now. So recognition, finding out what's there, this goes into questions about what should change, what's going to happen, and how could this happen. So thinking also about revamping scenarios or reuse of certain materials or building elements, imagining the object from one setting in another setting might be interesting area for future research. Okay, so I have reached the end of my presentation. I'm happy to take any questions and get inspired by your questions, of course. Thanks.
Great. Are there any first burning questions from the audience? Okay, a few hands.
Hey, thank you very much for a very nice presentation. I have a question about the first part of the presentation, because you showed like different references from different like researchers. Mm-hmm. And I guess there are some of the open source GitHub repos mm-hmm. that probably you use. And then the second part of the presentation was when there is a commercial setting with all the company and so on. So wondering like what happens in university versus like a real company. Do you still have their teams who actually, I don't know, training, for instance, the models to recognize, let's say, beams that you see in this image? Or you more taking from them from open source, or do you contributing back to academic setting? And the reason to ask is because there's a lot of good models that can recognize cats, dogs, bananas, and so on. But when it comes to these elements that are a bit more obscure, the rectangular and so on, there are not really good data sets to really work with. Yeah. That's it.
Yes, so definitely we have internal teams that are building AI pipelines because simply just taking what's in open source is not enough. Like you say, there's a domain gap, but there is also a gap with the data. You know, like it's large scale, it's high precision. So we have big teams that are taking care of designing architectures and preparing data and also training them. That said, in recent years, there is an enormous amount of output from research regarding those foundation models, and we have to leverage them as well. It would be a shame not to. So at the moment, I think we have a combination of leveraging open source models with appropriate licensing, obviously, and building our own. With respect to giving back to the community, I know that it's probably something that will benefit the research community a lot. There is always a bit question in companies regarding remaining competitive towards other players in the field. But it has happened in the past of Hexagon that we did release certain, let's say, traits that Hexagon itself has. So, for example, data, LiDAR data, was released as a data set, but now I think on the frontier of AI models, we simply are not at that level capacity-wise and competition-wise that we can give back in immediate context, yes. But we do try to share our knowledge with common research projects, maybe with collaborations with the Design++ lab and things like that, yes.
Then thanks for your nice presentation. If you are allowed to say that, I would be very curious to hear actually, what are you working on right now within Hexagon personally?
Yeah.
Yeah.
So I'm an AI researcher in a team, in the AI Hub team, and my task is mostly to understand what our stakeholders want to have in their products, and then linking the right research methods to it. So this might be from inspiration from papers, from open code repositories, new models, but also our own knowledge, of course. So that's domain knowledge from data perspective, but also AI knowledge on architectures and training settings. So in the end, I think from requirement understanding to conceptualizing the right research pipeline to executing it, that's more or less my scope of work. We have then more capable engineers than me that are able to productize such research level pipelines into something that is, workable also on an edge device, for example. Yeah.
Cool, thanks.
Okay, yes, thank you. There are a few more questions over here. I think I saw, is it you? Yeah. Okay. We'll do a round here. Okay.
Yeah, thank you, Fiona, for the talk. If I remember correctly, you had in your team quite shorter cycles than in research. I'm following up this research to industry gap, let's say. And if I know, or what you mentioned, you were testing different open source algorithms, comparing them internally, developing maybe your own ones. And when I looked at this product where you click on a scanned pipe and then it models the pipe automatically, I assume also the client wants to know what accuracy. So are you, for example, then also publishing, I mean, it would be good marketing or information for the clients to know with what accuracy can you count on, and then you compare it to other benchmarks, other algorithms promise, or you compare it to benchmark data sets. Are you doing this too? So publishing when necessary to make a client happy, and giving back to the research community also your results, or is that rather internal before it becomes a product?
So the accuracy or the precision at which our output comes is really important to our clients, yes, because I mean, you can use other scanning devices with less accuracy, which are cheaper, and so the clients that are with us, they're interested in this for sure. And an accurate kind of number on what is the precision, that's obviously also important. However, what we have noticed a little bit in this age of LLMs and agentic AI is that a lot of people start to understand what are the uncertainties of AI a little bit more. Okay, so the question of how accurate is this is a little bit it goes, I think, with the advancements of AI, and it has, I would say, not become less important, but product owners also and clients also understand better how they can work with uncertainty. So that's an interesting observation. In terms of a benchmark on modeling precision, if I understand you correctly, and then publishing it, we haven't done this before. It's maybe a good idea. Have to go with a data set also on LiDAR level precision. Yeah, so.
Okay. All right.
I will take it up as a point.
Thank you, Fiona, for your talk. Wonderful talk. So I have a question also about the pipes, by the way. So I worked quite a bit with point clouds, on point clouds in South Africa. We scanned thousands of square meters using terrestrial laser scanning. So we came into problems when we had to basically convert these point clouds into actual BIM models that would then be integrated into digital twins. So we experimented with some solutions similar to the one you showed on your presentation, such as, I don't know if you know Edgewise and As Built for Revit, the software plugins into Revit that try to automate the modeling of these elements in a BIM environment. But all of these solutions are always semi-automated, which results in quite a lot of time waste when we try to model pipes, walls, etc. So my question is, what is it exactly that stops it from being a fully automated process instead of being semi-automated? Because those semi-automated solutions still, from experience, were not working for us.
Pipes are tricky objects in the sense that they are very elongated and relatively thin. So having an AI system reliably, identifying pipes is probably the first kind of challenge. Then the modeling, I think, is always a little bit dependent also on what the user actually wants in his final kind of BIM model, in his final digital twin. So I can give you one example. Which country are you? Which standard pipe diameter is used in this country? It might be directly derivable from reality capture data, but given the noise in the point cloud and maybe the multitudes of different diameters, it might be difficult to just define what is the standard used. So I think one thing that at least we see is one of the inputs we need in the semi-automated workflow is really the selection of the standard that is used, being the DIN standard or American standard. And once that this is selected, the automation goes a lot further. So we can trace pipe traces with segments, elbows, segments, relatively automated, I would say. Can maybe, yeah, I think it's not worth it to go back. But anyway, I think like a few inputs from the users are so beneficial to the reliability of the process that we prefer always still to involve the user at that point. If you have ideas on automating that, maybe we can do this also in the future. Pipes are also, you know, the material of pipes is inherently reflective for the LiDAR, so it scatters the LiDAR beams. So there is a certain uncertainty that comes with the measurements around pipes, which makes it more challenging to choose those diameters. Yeah.
Well, thank you also from my side. I have a question. Actually, I would like to question your devotion to the reality scanner god.
Yeah.
Especially with the new young religion of the Gaussian splatting, whether that devotion has been questioned or reinforced. I mean, generally, there is the tendency of comparing the two technologies, although they're not really comparable for many aspects of it. But Gaussian splatting being this kind of very new tool where there's a huge amount of research has been done into it. How do you foresee reality scanning in this context of bringing, maybe merging the two technology? Or, because I mean, there is a certain advantages that comes from Gaussian splatting, the size of it, and so on.
Definitely,
I mean, what are your thoughts as an AI engineer on Gaussian splatting?
I am amazed by what is possible with Gaussian splatting, especially with the world models that are now being published by researchers with commercialized startups. Text generative Gaussian splatting with open vocabulary capabilities behind them is amazing. For me, it is still a visual representation of a scene, of a 3D scene. It might have information on what objects are, but in the end, to make them based in physics, those Gaussian splattings, there is still a long way to go. And that's where I see that point clouds from LiDAR measurements are much closer to what the reality is. Obviously, it's a relatively, even with open vocabulary capabilities, it falls short of what the reality really does, but so does Gaussian splatting, right? I think this age of generative models, which are pushed forward with Gaussian splatting, this benefits in the end the representational force of those foundation models. If you remember the bananas, how they aligned in this representational space, if generative models can imagine new spaces that are, you know, temporally consistent with physics, this will also mean that our representations in this latent space are also going to be physically consistent and temporally consistent. So I think Gaussian splats are a nice way to advance the technology. They look nice and they're convincing, but in the end they bring forward a bigger field of research which is more relatable than in the end to precision measurements and engineering tasks. Yeah, hope I answered this correctly. Yeah.
So I think we have time for one more question. I heard, and yes.
Thank you, Fiona, for the great talk. I think my question would relate to one of your outlooks about the need of precision for simulation and the question about pipes and the Gaussian splats. Because we've heard that all models are wrong, but some are useful, right? And all models are wrong, but some are useful.
Okay.
So that question of usefulness of the topologically precise, physically and otherwise correct models that we use in all the digital paradigm workflows, they're useful for that. So now you're working also in, forward-looking research, but also very hands-on in Hexagon as well. So my question is, would we need these topologically correct models or other types of models that are a bit more fuzzy, also like realities, very empirical and very tangible, very tacit, and our old way of modeling with this artificial precision, artificial cleanliness was based on all the methods, right? So would we still need this to take the decisions, to have useful assets and artifacts to take decisions in the future, or maybe it's going somewhere else?
It's an interesting thought, yeah. So saying that all intricate engineering models are actually, abstractions of the real world. No, anyhow, I like the thought. However, I think that there is a very big industry that is coupled to those models in the civil engineering, but in the manufacturing industry as well, and even not just the industry, but the ways we manufacture things are coupled to those models, right? In manufacturing, the way you cut a shape out of a block of aluminium, for example, it follows very clear topological paths and geometrical parts. So that said, I think if there is a radical way of innovating the whole thing, if we could start from scratch and have the freedom of redesigning everything, we would probably do things different, yeah. And I will take it as as something to dream about, yeah.
Thank you, everyone. I have, let's say, 2 points that I want to make. First of all, thank you very much again for your excellent talk and for taking the time to see us today. So maybe one more. And a bit of a thank you from our side. So then secondly, for the Design Plus Plus community, also if you're interested in what we do, next week on the 6th of May, we will host a affiliated research network meeting where we're calling it a scanning party. So we have an input from someone from Hexagon who will introduce different and say more hands-on intro on some of the measurement devices that you saw today, but also some of the software, etc., that are behind them. We will also hear a talk from a startup from here. It's vaulted, right? Layered, excuse me. We'll hear from Layered. They use a lot of scanning in their work, and then also from Professor Visa, who is, let's say an expert in the field. So come join us. We'll have some hands-on demos. We're going to have things you can check out, also talk to others about your own related research. So that will happen in the Bauhalle in HIF at 5 o'clock on May 6th. So let us know if you'd like to join or just feel free to show up. So thanks again and have a nice evening. Enjoy the apéro. It's right behind you. It's in the space behind the staircase. So thanks again.